let me start the class. Okay, the title of this class is spintronics. So I wanna start by the introduction of the spintronics in this morning. And as you know, our class is scheduled at the very early morning, 9 a.m. in Monday and Wednesday. So I know many students don't like this kind of earlier lecture, but it's the same for me. But the reason I'm scheduled this lecture in the early morning is after this lecture, I have more time. So if I schedule the lecture in the middle of the day, so I don't, I can use the time more effectively. So please accept this early schedule. Okay, my name is Chun-Yeol. I'm a professor of the disease in the Department of Emerging Material Science. And my major is about magnetism, and spintronics is closely related to the magnetism. Actually, this is very important sub part of the magnetism. Okay, so let me start. What is the spintronics and why we have to study the spintronics? Okay, so in this view graph, you may see the some cartoon is the cover of the Nature Materials, which is the one of the most famous journal in science, in material science. And there are many words, and this word is kind of statics of the papers, which one is the published in Nature Materials. And the bigger font means it's more frequently handled in this journal. So as you see here, the magnetic and spin is one of the most important topics in material science. So that implies the magnetism, the spintronics is one of the main stream in research in material science. And also there are many related topics with the magnetism, like nanoparticles, nanowires, and ferromagnetic films, and anisotropy, and so forth. So in this lecture, I will give about this related topic called the spintronics. Okay, so maybe many students are already familiar with the name of the spintronics, but let me start the very basic of the spintronics. Spintronics is kind of the new word combined by spin and the electronics. Okay, so as we hear, the electronics is one of the important technology in a modern society. Without electronics, our modern life is impossible. And there are, conventional electronics, as you know, is based on the semiconductor, and they are all based on the electron charge. All electronics device is designed to control the electrons of the charge. And the charge is one of the most important property of the electron. But we already know there are one of the most important fundamental property of the electron called the electron spin. You already know about what's the meaning of the spin. Electron is actually, we can deal on electron as a very small magnet. And this magnet can be aligned to specific direction, we call the up or down direction. So that means when we control the electron charge by the conventional electronics, and if you have additional control of the electron spins, that's we call the additional degree of freedom. That means we have a more functionality of the device. And also, as you see here, the spin is aligned up or down So that means there are very well-defined two states called the binary state or up and down state. And that means it is very, very suitable to describe the digital information. And in addition, the spin state is persistent. Here, the persistence means if you assign one direction of the spin, they will keep their direction without, if you didn't give any perturbation. So that means if you once write the information, they can stay. So that's the very basic of the information storage. But as I will gonna explain, in many kind of memory device like DRAM, it's not they cannot stay forever. The information stored in a DRAM will be disappeared within tens of microseconds. So that's called the volatile memory. And in the other word, this spin memory is basically non-volatile. That's the very, very important memory applications. And in this sense, the spintron is plays a very important role in storage. But in current stage, there are many research about the logic application, logic operation, and transfer of the information. So there are many applications of the spin devices, and I will gonna give a lecture about this. So I just give a brief lecture for one page of view graph. So as I already said, the online lecture is not very convenient for the lecturer and the student. So far, is it okay, or do you have any problem to hear? Please type your message if you have any problem. Okay, sounds good. Okay, I will keep going. Okay, before we go into more details of the spintronics, I'm gonna briefly review about the modern electronics. The reason is, here there are some old word called know your enemy and who you are, then you will never lose. For the Korean student, is very, very well-known word. How about the Big and Lia? Have you ever heard about this word? Yeah. Lia maybe heard about this because it's very well known in Asian country. So anyway, so it's kind of a thing. If you know your enemy, here our enemy is not the modern electronics, but anyway, we have to compete with the modern electronics. So we have to understand what's going on in a modern electronics and what is the limitation of the modern electronics. So it's very not closely related to the spintronics, but this lecture, this topic will be very helpful when you wanna apply to some electronics company like a semiconductor company. Okay, so let me start about this. Modern electronics, you may see there are many devices like modern computers and smartphone and display and camera and game player. There are many. And one of the most common point of this all electronic device, they have a small chips inside of them. So we call this is IC. This is the acronym of the integrated circuit. As you see in this cartoon here, there are so many small pieces, and they are all connected by the wire. And this is called IC, and this is kind of building block of this modern devices. And all these small IC can be categorized by these 4 categories. Actually, there are something more, but I just simply categorize these 4 types. One of the most important things is information of the storage of the information called the memory. There are many kinds of memories. like DRAM, we store the memory but for the very short time, and or cache memory, they are all even shorter time. And there is some logic operation of the information called the CPU, the central process unit, or AP. This is for the mobile one. It's actually the same concept of the CPU and AP. And we have to transfer the information between this IC or each equipment, like a cellular phone or a modem or Wi-Fi or Bluetooth. They are all related to the communication of the information. And even the not only for the between the equipment, but between the IC, there are many small lines. They are also transfer the information, or sometimes they transfer the power. And also, we have to say about the sensor. For example, you can see this small dots moving by my mouse. Mouse is kind of the sensor or input device. That means the sensor is connected to the this electronic device with the outside of the electronic device. So mic or this mouse or there are many sensors in modern electronics. They should communicate with the human being. Okay, so the reason I categorize these four types of this blocks, because all these four types, the magnetism is contribute. I made the red font for the memory and sensor. In the memory and the sensor, the magnetic devices played very important role. But in a CPU, there is no contribution of the magnetism, but we are working on it. We want to make some CPU operated by the spins or AP. And your communications, there is no enough room for the spins, but there are some study also about these communications. That's the reason I'm using the different color. Okay, so during this lecture, if you have any question, please raise your hand first. Then I will give a mic for give a chance to ask any questions. And also, after this lecture, I want to have some time to the all student. You should give at least one questions for each lecture. So this lecture is scheduled for 75 minutes, but I will try to finish my lecture within the 60 minutes, and we have 15 minutes more. Then every student should ask at least one question. Is it okay? Yeah, any simple question is fine. So don't be afraid about that. Okay, so here I will show the some cartoons for the diode. You know, in a diode, you may learn about this diode during when you was in undergrad course, and also you may learn the transistor, and also you may heard about the CMOS. They are very basic building block of the modern electronics. So you should understand what's going on in a diode and the transistor and what is the CMOS. And you may see this kind of figure in your semiconductor lecture. And there's a p-doped semiconductor, and there's an n-doped semiconductor, and there is some deflection layer, and the current can be passing through only one direction. This is what you learn about the diode. And if you combine two diodes by the NPN type or PNP type, you may build up the transistor. And this transistor, using this transistor, you may amplify the signal, or you may switch on and off by the control of this transistor. And you may familiar with this photo. You may know this is the transistor. And what is the real shape of the transistor in a modern electronics? In a modern electronics, this is a NMOS, this is PMOS, and as you see here, there is one common substrate, and there's a p-type doping and n-type doping and another n-type doping. And here is a large n-type where, and there are p, p, and n-type. This is the real shape of this most transistor in a modern electronics. So please forget about this shape or this shape. This is a reality. So as you know, in modern electronics, can be explained by very simply by the Moore's law, who is the co-founder of the Intel company. And according to this Moore's law, there are very rapid increasement of the performance of the electronics. And in this cartoon, you may see from 100 years ago, the number of the transistor increased very rapidly. This is even faster than the exponential growth. So this is very early stage of the computers. You may heard about this Univac or Apple II is very old style, and Power Mac is built up in a end of last century, and this is nowadays. And we believe that the performance of the computer is surpassed the brain power of the mouse in this year. And many people predict even the computer's power can overcome the human brain power in near future. And as you already know, there are some artificial intelligence, and even in a very specific field, the AI already overcome the human brain's power. And what's the behind of this amazing improvement? This is a kind of a map of the number of transistors in a single chip by the year. As you see here, this year is a linear scale, and the y-axis is the number of transistors in a single chip, is the exponential scale, the log scale. So this is the almost linear. So that means they are starting from 1,000 chips in 50 years ago, but now we have more than billions of chips, the transistor in a single chip. So this is the history of the computer. This is the code of ENIAC, the electronic numerical integrator and computer. It was born in 1946, and they have 18,000 vacuum tubes. So as you see here, it's very bulky, and there are huge number of wires, and these people try to connect the wires, or maybe he is repairing these computers. So anyway, in this time, they are using the vacuum tube. This is the ancestor of the transistor, and they consume a lot of power. So in order to operate this kind of large machine, you need a separate power plant. And about 20 years later, it's 1964. There are a computer called the mainframe. This is operated by IBM, and the Apollo project is operated with this mainframe. Oops.
코로나19 대책반에서 알려드립니다. 외부 지역 코로나19 확진자 발생에 따라 텍시스 코로나19 대책반에서는 바이러스 감염 예방을 위하여 외부인 방문 시 가장 먼저 대학 본부 및 연구 행정동의 안내 데스크를 반드시 방문하여 발열 체크 및 호흡기 질환 이상 요율 확인 후 안내에 따라 해당 건물로 이동하여 주시기를 바라며, 또한 임직원 및 학생들은 마스크 착용, 손 씻기 등 개인위생 수칙을 철저히 지켜주시기 바라며, 발열, 기침, 호흡기 증상이 있으시면 반드시 대책반 상황실 또는 가까운 보건소로 신고하여 주시기 바랍니다. 다시 한번 코로나19 대책반에서 알려드립니다. 대구 지역 코로나19 확진자 발생에 따라 디지스 코로나19 대책반에서는 바이러스 감염 예방을 위하여 외부인 방문 시 가장 먼저 대학 본부 및 연구 행정 동의 안내 데스크를 반드시 방문하여 발열 체크 및 호흡기 지원 이상 요를 확인 후 안내에 따라 해당 건물로 이동하여 주시기를 바라며 또한 임직원 및 학생들은 마스크 착용, 손 씻기 등 개인위생 수칙을 철저히 지켜주시기 바라며 발열, 기침, 호흡기 증상이 있으시면 반드시 대책반 상황실 또는 가까운 보건소로 신고하여 주시기 바랍니다. 감사합니다.
May I have your attention, please? As a confirmed case of coronavirus disease 19 has occurred in Daegu, DGES Task Force on Coronavirus Disease 19 is asking your cooperation. Please let all visitors check respiratory symptoms including body temperature at the information desks in the lobby on the first floor of B1 or R1 buildings upon arrival. Also, please wear a mask and wash your hands frequently for your safety and health. If fever or respiratory symptoms such as cough or sore throat appear, please make sure to consult with Situation Room of DGIST. Call the nearest public health center or 1339 first. Repeat again. As a confirmed case of coronavirus disease 19 has occurred in Daegu, DGIST Task Force on Coronavirus Disease 19 is asking your cooperation. Please let all visitors check respiratory symptoms including body temperature at the information desks in the lobby on the first floor of B1 or R1 buildings upon arrival. Also, please wear a mask and wash your hands frequently for your safety and health. If fever or respiratory symptoms such as cough or sore throat appear, please make sure to consult with Situation Room of DGIST. Call the nearest public health center or 1339 first. Thank you.
Okay, I just start the lecture during this announcement. Okay, so let me ask a very simple question. In this photo for the main frame, you may find very many strange machines for you. For example, this one is kind of a tape recorder. There are some reels. It's magnetic films, magnetic recording, and each reel, as you see here, this woman, they should change the reel when they want to access some specific data. And there's some kind of a typewriter, and this guy is kind of operator. But did you see a monitor of this machine? Actually, in this time, there's no monitor. There is some kind of output by the kind of printer. So in this time, most of the operation is kind of calculation. So the coding is done by the key puncher. You may never see. So anyway, it's a very old type. And here, there is a first supercomputer called from the Cray company. It's about about 50 years ago. In this time, this supercomputer used to many engineering calculations. And at the same time, by the Wozniak, the first Apple appeared with the small monitor and the keyboard. It's very cute. And if you may have the original version of Apple, it may cost a lot nowadays. You can find this kind of machine in only museum. And first IBM PC was appeared over 40 years ago with the personal monitor and keyboard and the body. This the first personal computer is basically same with the modern computer. Okay, now most of supercomputer made by a cluster, and they have nowadays most of supercomputer consists by 3 million cores. not the transistor, 3 million cores. So each core has a billions of the transistor. So the total number of the transistor in this kind of cluster computer is an amazing number. So let me back to the long time ago in the sense of the history of the CPU. In a first very common CPU called Intel's 8086 was born in 1978, and their operation clock speed is around 4 to 10 megahertz. And please pay attention about the number of transistors. This is already 29,000 transistors. And as you see here, the ENIAC, the very early computer, it's very huge machine, but they have only 18,000 vacuum tubes or 18,000 vacuum tubes in this large machine. But after 30 years, we have even number of transistors in a single small chip. And 10 years later, the number of transistors is getting larger, more than 10 times. And but the operating speed is still megahertz. And after 10 more years, the number of transistors increased to 3 to 4 million transistors for single chip, and the clock speed is now over the 100 megahertz. And for the Intel Pentium 4, the operating speed now over the gigahertz range, and they have more than 10 million transistors, and this is 64-bit CPU. And it's not very cutting-edge CPU, but the Intel's, for example, Intel's Core i7, I think I made this view graph few years ago, so this is now old type. But anyway, there are many multiple cores in a single chip, and 64-bit CPU, and operating speed is 3 gigahertz, and the number of transistors is now more than billions. And also, I write down some number, the length scale of the 14 nanometer. This is the called the gate line, or the size of the pattern in this CPU. Okay, so compared to this CPU, I want to check the history of the hard disk drive and the heads. This is the very old style hard disk drive, and this behind in the backside, a very huge machine. And this is the first, almost the earlier version of hard disk drive, and it's very bulky. And the modern hard disk drive is something here. So the size of hard disk drive getting smaller and smaller, like a chip size. And the capacity of the hard disk drive can be described by this simple plot. As a number of the production year, the areal density means how many information you can store in an inch scale. So the large number of the areal density means we can store more information in a single disk. And as you see here, they are starting 1950 something. They are starting with actually 5 megabyte, and they are increasing the capacity very rapidly by this is the log scale. So this linear scale means actually is exponential growth. And even in some specific year, the slope is getting steeper. So that means there is some technical breakthrough. With some technical breakthrough, we can even boost up the speed of the increasement. And as you see here, this is a long time ago. We are already here. But the reason I'm showing this one is this is a long history of development hard disk drive, and this is a new version of the same one. This part is the earlier version. And as you see here, the unit added density is changed from the megabit per inch square to the gigabit per inch square. With the megabit inch square, we cannot describe this modern technology. And also, when I studied this in this year, there are many limitations, physical limitations called superparametric effect. So many researchers predict, oh, there is some limitation of the hard disk drive because of this. This is a fundamental limitation. But somehow the engineers and scientists overcome this limitation of the magnetism by introducing new technology. So even there is some breakthrough and there's some change of the slopes. And this error density described by the terabit per inch square, not the gigabit per inch square. So there are still progress in a hard disk drive company, but frankly speaking, this is almost getting limited. Now, the error density of the hard disk drive is almost saturated. So now the 1 or 2 terabyte per each disk is, I guess, is almost limit. Even though we overcome this limitation, we can make 100 terabyte or even the larger capacity for the hard disk drive. But anyway, who knows? Somebody make a very good idea and make a big breakthrough. Maybe you can keep going this development. But it's same in a semiconductor company. You may already notice that the clock speed of the CPU is already limited. About 10 years ago, the clock speed of the CPU is already 3 GHz. Now it's almost same. We cannot make an even faster clock speed. Instead of that, the CPU company decided to make a multiple core to enhance the performance of the CPU. So we may make another idea to boost up the density of the hard disk, capacity of the hard disk drive. Okay, but still, we are still hungry to store the more data. This book is written by IDC. This is the very famous company who is this kind of research company for the market. So it's about 15 years ago. Many important storage company wondering what's going on a digital storage. So they asked to this company IDC, and what's the future of the data storage? So this is the report written by this market research company, and this is like a big bang. So the title of this book is Expanding Digital Universe. So what's the meaning is the information storage, the demand of the stored information, the storage capacity for the digital information is getting increased even faster and faster. You may easily understand these things by your personal experience. Probably you may have your first smartphone about, maybe 5 years ago or 10 years ago. At the time, your memory of your smartphone is maybe much smaller than nowadays one. And how about your photo image? The quality of each photo is getting larger, and the quality of your photo is getting better and better, means they have an even larger size. And by the development of SNS, if you upload one image, the image is shared by many your friends, and they are duplicated by the total capacity of the storage in the world. If you download your friend's photo, that means the image is stored in somewhere in your smartphone or your cluster. Somehow your data is stored in some place. So that means total number of the total capacity of the data storage is getting increased fast and fast. So that means we need more better information storage devices. Okay, so let's back to the history of the transistor. These guys, three guys, name of the John Darwin, William Shockley, and Walter Brettin, they are the Nobel Prize winner for the transistor. And this left cartoon, can you see the zoomed image? Okay. This is the replica of the first transistor, and as you see here, the first transistor looks like some very weird wiring. This is kind of a single crystal of the, maybe, I don't remember, it's a silicon or germanium. Anyway, single crystal of the semiconductor, and there's some contact. So this is the very bulky and very large scale, but they're working as a transistor. But nowadays, the most common, sorry, this is the this number 69 to 49 to this number means the gate line, and this is the real photo of the modern transistor. So from this old style transistor to this modern style transistor, there are many developments. And this number is we call the gate line. Is you can imagine the modern IC is to build up the modern IC, you need very fine patterning, and very fine patterning. If you make a fine pencil, you can make a small. You can draw the small figure very with fine pencils. If you have a more small and more fine pencil, you can make a more small figure. It's same. If you're using the small pattern size, you can make more smaller devices. Then you can increase the number of transistors for each devices. So that means you can boost up the performance of your chip. So let's see these two photos. You can easily find these two photos almost the same, but there are big difference. This is the 128 megabyte, but in the same size, we have a 128 gigabyte of the memory. Yeah, it takes only 10 years to make a 10 times the larger capacity of the memory. So it's really amazing speed of the development. And even this is the very old photo, more than 10 years ago, but you can see this is the single grain of the rice. It's very tiny one. And this is the CPU of the called Atom, is for the mobile application. They have 47 million transistors in this small chip, and 45 nanometer line width. And yeah, this is too much details. Anyway, so now you can imagine about 12 years ago, they are using 45 nanometer node, and they predict this kind of prediction, 14 nanometer technology. The scale can be the size is scaled down to 1 to 8. Now you may see some report about less than 10 nanometer technology. Even the Samsung and the TWMS, they succeed to produce 7 nanometer technology. So that means even 1/16 size drop compared to this one. And this is the very modern, the shape of the modern transistor called the pin-type transistor. I'm going to explain more details in the near future. But as you see here, this is 20 nanometer, and this is 15 nanometer. And this fine structure, you should make this, even this is a smaller, it's a 5 nanometer scale. You should make this kind of structure of the billions of this one to build a one CPU. So it's kind of art. So before going for more details, I'm gonna explain the very basic function of the DRAM. I hope all students know about the DRAM. Do you know what's the DRAM? Please answer me. There is no response, so it's very difficult to give a lecture. Okay, so the very basic one is enough. Okay, so I'm gonna explain not very details, but very basic part. The DRAM is called the main memory in your computer. When you buy your computer, you should think about how much memory how much main memory you need. So most of the affordable computer nowadays is 16 or 32 gigabyte of the main memory. So this main memory is you may read your data from your hard disk drive or SD, solid state memory to the DRAM. So this DRAM, the DRAM is kind of the working desk. When you are studying, you can bring your book or note and from the shelf to the desk. And after you finish your study, you may bring back the books or note from the desk to the shelf. So desk is kind of a temporary working place. So DRAM is kind of a temporary memory to operate something. So this DRAM we don't need to store the information to the DRAM. Okay. So here the DRAM, this we have a 16 same element. They consist by one capacitor and one transistor. We call this is 1T, 1R model, 1T, 1C model. So here this transistor is kind of a switch. And if you close this switch, you may store the charge in a capacitor. So if you stored charge or not stored charge, so that means if you can read the charge in a capacitor, if there is some charge, we can assign this is 1. And if there's no charge in a capacitor, we can assign to 0. So it's kind of binary memory. So in order to read this capacitor, you should close the gate, and if there's some charging, then the charge particle is passing through this line. So you may read some current if there is some charge. And if there's no charge, there's no current. So you can distinguish it, there is some stored charge or not. But here, there's very, very important weak point. When you read it, the charge is disappeared. So we call this is a destructive reading. So that means when you read, you lose your information. You lost your information. So you should rewrite this information again. And also, when you store the charge in a capacitor, and if you have this transistor, this is not a perfect gate. There are still finite chance the charge escape from this capacitor passing through this gate. So it takes 60 microsec in modern DRAM architecture. So all information stored in a DRAM will be disappeared within 60 microsec. 60 microsec is very short time for the human being. But in a modern computer, as I already said, they operate by order of 3 gigahertz. 60 microsec is very, very long time. So, but still, after 60 microsec, the stored memory must be rewrite again. So there should be larger consumption of the power. That's the reason when you turn on your notebook without anything, you didn't do anything, but they are still consume your energy because of this rewrite process. But if you think about your cellular phone, if you didn't do anything, then they keep their memory because they are using different memory key called non-volatile memory. With the non-volatile memory, the data is stored once, then they are still they didn't disappear. So anyway, please keep in mind, DRAM is made by one transistor and one capacitor and large array. This is now 16-bit array, but if you have a gigabit, how many this kind of array do you need? You can easily imagine 10 to 9 number of this small transistor and capacitor. So I want to recall this relation. The capacitance of the single capacitor expressed by this equation. The epsilon is the dielectric constant of your material, and A is the area between these two parallel plates, and D is the distance between two parallel plates when we think about the simple capacitor. So this is called planar capacitor. In this planar capacitor, we have two electrodes, and as you see here again, there's some capacitor, and there's a transistor. This 1T memory cell, this is represent this part. And if you make a small, this one, you can make a large memory. So here, this red one is called the capacitor. But if you make a small and small, then this A is getting smaller and smaller and smaller. Then the capacitance means how many charge you can store is getting smaller. So that means you should keep this capacitance to maintain the charge. But in order to make a small capacitor, you should decrease this A. So there's some limitation. Okay, so so people try to make a smaller capacitor, but they want to keep this capacitance. So there are two strategies. One is they make a stack of the capacitor by this multiple shape, or they make some cylinder shape to keep this area. And as a result, this kind of very strange shape of the capacitor is modern DRAM shape. As you see here, this very long capacitor we call trench, they are kind of long cylinder. So we can make this kind of a capacitor by make this small, but this is long. Then you can large area to maintain the specific value of the capacitance. So we make a transistor in a very bottom and make a very large, long cell capacitor to keep this the performance of the DRAM. And you can easily compare this DRAM capacitor with the Burj Khalifa, which one is the most famous building. And the height of this Burj Khalifa is 800 something, and the bottom is 100 something. The ratio between the height and the bottom, we call the aspect ratio, is only 6. But DRAM, the capacitor is bottom size is a few tenths of nanometer, and the length is more than micrometer. So the aspect ratio is more than 25. So you may see real photo. This is a 3 micro something, and this small length is a tenth of nanometer. So this is the single cell of your DRAM. You can store 1 bit in this capacitor, and you should make billions of this for 1 gigabit RAM means you should make a 10 to 9 capacitor, and they should be working. So it's kind of amazing technology, and even they make this kind of structure in a very large wafer. I mean, I'm gonna explain later. So if you make this single chip, you need a successful matching of this capacitor, so 10 to 9 or 10 to 10, and that consists only one single memory. But in a semiconductor company, they should put this single chip, the huge number of chip in a single wafer. So in a single wafer, nowadays is 12-inch something. Then you can easily calculate how many capacitors you should make it in a single wafer. It's a huge number. So anyway, so now I already said I'll give a 60 minutes lecture. So I'm gonna hold my lecture here, and this is time for the questions for today's lecture. Today is the first day, so you may ask any casual questions. That you shouldn't relate it to this lecture very closely. You may ask about some the fundamentals, or even for the personal question is fine today. Okay, so we're gonna start. You may use your mic, or you may type in a chatting program. Okay, please.
Yeah. The PowerPoint you are showing us, will it be somewhere? So can we get it somewhere, or is it just for the course and we have to take notes for the rest?
Sorry, can you say again? I didn't catch you.
What you are showing, like the slide.
You mean
will
the
it?
slide?
Yeah. Will we have it? Like, will it be on the LMS so that we can get it and look at it again, or is it just for the course?
Yeah, I'm gonna upload this pop. I wanna upload after the lecture because there is some questions during. I can find some kind of questions during the lecture, so I'm gonna upload it after finish my lecture. Is okay?
Okay.
You can download.
Perfect.
Yeah.
Fine. Thank you.
Okay. Okay, Gina, please tell us.
About the Moore's law.
Sorry, I cannot hear you.
How about it? How about this?
Yeah, it's okay.
More okay.
Yeah.
Okay. I have a question about Moore's law.
Mm-hmm.
Actually, I have been had this question a lot before.
Mm-hmm.
I want to know about the meaning of Moore's law because I thought it's just for expecting the future inclination.
Yes, exactly.
It's just for expecting the future inclination.
Okay. Moore's law is not the scientific law. It's kind of, as you said, it's kind of prediction by the Gordon Moore, who is the big guy in the semiconductor industry. After he built up the Intel, and he saw some trend of the development, and he found okay, the number of transistor in a single chip is increased by double for every 18 months. At the very earliest, is the kind of trend. But after he more claimed that kind of rule, this is not the real law, but many company owner want keep this law, and they make some plan to based on this law. So they really push the engineers to keep this. So Moore is a very famous and very important guy in the semiconductor industry. But most of the engineer in the semiconductor industry, they really hated that guy because they want to really keep this law. Even in Wang, who is the one of the president in Samsung semiconductor company, he claimed the Huang's law, and he claimed the density of the number of transistors should be doubled for every year. So that make the engineer crazy. I heard them kind of a story. The president of the semiconductor said, okay, so we're gonna have a result in this, let's say, December. We're gonna announce we developed the double capacitance compared to the last year. Before the engineer got their result. So that means the semiconductor industry engineer should work harder and harder. So somehow they keep this law for a long time. But we strongly feel this is getting close to limitation. That's why we need a totally new device like a spintronics. So the Moore's law is not real law. It's kind of a prediction, as you mentioned. Yeah.
Okay.
Is it enough?
Yep.
Okay, so okay, for the last question, this is very good question. Actually, this is the kind of error in a process. This process is kind of etching process. Even though we used to really expensive and very careful machines, there are still kind of a deviation. As you see here, this length is very like 10%, and that means as you see, if you see closer, the radius is also there is some kind of variation. So it's kind of the variation of the length and the depth and the radius, but somehow they keep the certain tolerance range of the capacitance. Then it'll be okay. So if you want to reduce this error, it costs more. And then some, it's kind of a engineering talk. So if you allow the certain error range, the cost is getting down. So there are some kind of optimization. This is what I understand. Is it okay, Leah? Okay, Won-Chang. DRAM is the one of the main part in semiconductor industry, and I don't know the exact the percentage, but the memory in the semiconductor industry, memory is means usually DRAM. It's about 20 or 30% something, and the non-memory means the CPU. So that's also about 30% something. The reason Samsung make a lot of money is because of they make this DRAM or flash memory. The flash memory is also another big market. So modern car is operate with DRAM. Without DRAM, you cannot operate the modern computer. So DRAM and flash memory and CPU, and there are something more, but they are all important in a semiconductor industry. Yeah, but the importance of DRAM is getting smaller and smaller. That's why the Samsung and many semiconductor company want to make a new non-memory applications. Okay, for the Dong's question, the spin state is generally, if you set your spin direction, they are keep their direction. So that means there are two meanings. One is in the quantum mechanically, the spin direction is actually there's some probability functions, but if you well define the state, they are keep their state without any disturbation. And also in a macroscopic region, I'm saying the spin means the direction of the magnetization. If you assign one direction of the magnetization, they are keep their direction without if we didn't apply any magnetic field. So that's what I mean in the persistent. Okay. Okay. For the Changa's question, the ratio means scientifically it's nothing. I just wanna say it's a difficult one. You know, this aspect ratio of the 25 is technically very, very difficult. If you have any experience of the patterning, you may imagine how you should make a deep trench, deep holes with this aspect ratio by the etching process. It's amazing technology. Good questions. Okay, I got my first one when I entered my university. So I think it's about 33 years ago. So at that time, I have a CPU of the 286. This is the earlier version of the between the 886 and 386. So it's about, when I bought my first computer, the computer seller told me you never need the hard disk drive before you graduate. So yeah, at that time the price of a computer is very, very expensive, and but still they don't have a hard disk drive, and I have only floppy disk drive, and I cannot do many things with them. Anyway, so yeah, it's really long time ago. How about Taeyong? What is your first computer? Okay. Yeah, I started with the DOS, the disk operating system, and yeah, it's too long story. Okay, so yeah, it's almost time up. So is there anyone who didn't ask any questions? I think. Actually, I don't understand your question. What's the meaning of the compounded input and output system? Compounds? Tail, do you have a mic? If you have a mic, please use the mic. You may ask question by the Korean. Yeah, I know what you mean, but still I don't understand your question. Okay, yeah. Actually, IBM personal computer PC is the very wide, just kind of, they, how can I say, modern computer, they consist by the keyboard and mouse and, monitors. And very first part of the beginning of the IBM PC, there is no mouse. This kind of optional devices. Anyway, but it's pretty much kind of a standard of the modern computer. Yeah. But there are many different models. So, but IBM PC is kind of the starting point of the modern PC. Maybe that's the right answer. Okay, so I think it's time's up. So, next Wednesday, and not next Wednesday, this Wednesday, we're going to have a next lecture, and I'm going to share my PowerPoint in a LMS system. So, see you in next Wednesday. If you have any questions, you may use the KakaoTalk after the session. Okay?